Thank you all for being here over lunch. I appreciate that so many of you forewent your food to be here. I'm going to talk a little bit today about some of the efforts that Boeing Digital Aviation Solutions is doing to get streaming data onto the FliteDeck and how Databricks has helped us do that. I'll start with just a quick introduction to myself. I'm a data scientist, primarily concentrating in flight operations at Boeing in the Digital Aviation Solutions Group. I have a background in mechanical engineering and operations research. I actually started in the elevator industry, and it was a great learning experience in what not to do with my career. It turns out no one calls you because their elevator is working to say thank you so much. I just want to let you know it's still going up and down. But in that career, I encountered some other really interesting problems. Like, how do you route a mechanic to get around to all the buildings that they need to do maintenance on in the shortest time frame possible? How do you deal with interruptions that come from service calls and things like that? That led me to the traveling salesman problem, and to operations research, and eventually to data scientist. Probably my most important thing right now, I'm a dad and a Dachshund owner, wiener dog. And right now, my goal is for my daughter to stop beating my dog as the loudest barker in the house. Boeing's a huge organization. It's grouped into 3 divisions. There's commercial aviation, there's defense and space, and then there's services. I'm part of the services group, and in that group, there's a Digital Aviation Solutions that builds software for airlines, for aircraft operators. Things like Jet Planner for flight planning, which route you're going to take, how much fuel to load on, aircraft performance, taking into account their winds, things like that. FliteDeck Pro, which replaces 40 pounds of paper that pilots used to carry with them on the flight deck, with an iPad that has all their charts and things like that. My team is part of the data science group, and we've been involved with some products like crew calibration, which is dealing with your crew pairing problem and trying to balance the optimality of your optimization of how do you assign crew with the robustness of once you actually get to that solution and go implement it or go operate it, how likely you are to actually be able to do it. And then most recently, Insight Accelerator, which is allowing data science teams at airlines, engineers at airlines, to use their quick access recorded data to do predictive maintenance, to try to turn unscheduled maintenance into scheduled maintenance. The group is about 40 folks. My team primarily works in the flight operations space. There's just a few of us on this team. It's a great, small team. And I'm going to talk to you about a use case and how Spark helped us bring it to market. Okay, so you're a pilot. You're preparing for a flight from Vancouver to San Francisco. I'm based in Vancouver. I assume my pilot did this on the way down here. You'll have your flight plan briefed. You know your route, your departure procedure, your arrival procedure. You have your fuel on board. You have all your passengers. You're ready to depart, and now you have an opportunity. And that opportunity is, should I perform a reduced engine taxi out? Reduced engine taxi out, for those who aren't in the industry, is kind of like the mother of all cylinder deactivations. So you can imagine on your car can sometimes turn off a cylinder to save fuel, but you can actually taxi out with only one engine running to save fuel. How useful is it? What kind of the impact is, or what is the impact of it? It turns out pretty powerful. When you're doing your taxi out, you start at your stand departure. You want to get to your runway departure. The last few minutes of your taxi out always needs to be running both engines because you need to take off with 2 engines. And you need some amount of time for that second engine to come up to the proper temperatures and pressures before you take off. But before then, in some instances, it's possible to operate with only a single engine. And there's a big difference in fuel consumption during that time. So when you're taxiing on a single engine, this is data from one of our customers operating 737s, just averaged over about a 6-month period for taxiing out. We can see fuel flow on a dual engine taxi out is somewhere 1,700 to 1,800 pounds per hour. On a single engine, about 1,000 pounds per hour. so significantly less. If we translate that to something that makes sense to me, because I don't think of fuel in pounds, I think of it in gallons. We're talking about 150 gallons versus 270 gallons. So if we take a scenario where you're taxiing out for 25 minutes, you do that all on dual engine, you'll burn 112 gallons of fuel. If you can reduce engine taxi for 20 minutes, you could burn 50 gallons during the single engine. You burn another 22. That's 40 gallons of savings on that taxi out. Now that sounds to me like 2 times that I could fill up my car. It's a reasonable amount of money to be able to do on a flight. And if you can do that on every flight, the savings add up. In fact, if we look at a moderate-sized operator, about 80 to 100 tails that can do this, over a year you might save about 4 million tons of CO2, about $5 million in fuel. That's the opportunity. Somewhere around 20 to 30% taxi fuel reduction. So you might be asking yourself, why not always reduce engine taxi out? So why not always RETO? Well, it needs to be part of the standard operating procedure for the airline. Your aircraft needs to be capable of it. Sometimes there's restrictions about which engine you can start based on systems on the aircraft. The aircraft itself can't be too heavy. Otherwise, you might need to use too much throttle. That'll create jet blast, which would cause damage at the airport. After that, though, you really have to come down to just time. So how much time do I have? If there's only a few minutes, you don't have time to go through that whole procedure. You might as well just start both engines now. If it's going to be longer, then you might have that opportunity. But as a pilot, if you get to the runway and your engines aren't warmed up and ready to go, you're going to have to sit there and wait. Or you're going to get asked to move somewhere else, and then other people are going to take off, and your taxi time is going to go further. So in the absence of really good information, we think pilots don't do it as much as they could. So as a data scientist, put on my data science hat, it sounds like a data problem to me. Can we come up with better data about taxi out? Turns out probably, but it's not easy. Aviation is a very fractured data landscape. There is a tremendous amount of data available, but it varies and it's very heterogeneous. So depending on which airline you are, which airport you're operating out of, which region and which air navigation service provider, you might have all different sources of data. Some will have similar things. Some will have things that seem similar but have totally different definitions. Whatever it is, the accuracy can vary. And our solution for a tool like FliteDeck Pro has to be global. We have to be using the same thing all over the place. So there is one source of data which is really ubiquitous, which is global, which is always the same, and that's ADS-B data. ADS-B is automatic dependent surveillance broadcast. It's a transponder on the aircraft that sends out like, hey, this is my position, this is my altitude, this is my speed, I'm this call sign right now, squawk code, all kinds of things. And as an aviation enthusiast, you can host a receiver for this. I have a little PiAware, so it's like a Raspberry Pi plugged in with a software-defined radio, and I collect ADS-B data and I send it over to FliteAware in this case. You can do that too. And we can provide that data. We can get that data from one of these suppliers. We get about 250,000 different flights per day, about 10,000 records per second coming through. Ton of data. Kind of looks like this. And I wanted to put data up on the screen. This is one flight taxiing out. And if you're really good, you could probably go in and see, okay, like the speed is low at the beginning, and then it's coming up at the end. The heading's changing a little bit. It's hard to make heads or tails of what this data really means. But one of the sources of data that we have is Jeppesen nav data. Jeppesen nav data is a global leader in aeronautical data. Charts, procedures, all kinds of things. We have waypoints, airways, all that kind of stuff. In fact, Jeppesen processes like 46,000 incoming documents every AirAct cycle, which is the 28-day period that this data is updated, from, I think, 195 countries, 24 different languages, pulls this all together. One of those great data sources is our airport map data, where we have really, really detailed polygon representations of the airports, the runways, the taxiways, the stands, the de-icing pads. and the topology that connects them all together. It's really a fantastic source of data. So when we take those two sources and we put them together, we go from this, we go and we can add on a little bit more, and we can get a much broader picture where now this aircraft is very clearly starting at a stand, starting to push back, starting to move forward on its own power, taxiing, getting to the runway, and starting to take off. It's pretty straightforward now for me to just go in there manually and say like, oh, great, aircraft pushed back at this time, got to the runway at this time, this line to taxi out, good to go. By the way, this visualization, if there's any developers in here, we've been working on something. Oh, it doesn't show up. But we have a little library that we build, deploy that to a Databricks workspace, and then you can import that library and really quickly create some complex visualizations. So much nicer in my perspective than having a notebook that you're like, oh, do you have the latest copy of the thing that does that visualization? So we just share the library, you import a function, the function knows all the data in your tables, goes and grabs it and can plot a flight or whatever you care about in this case. So just a little tip, this is a developer conference. So how do we do this for more than one flight? Well, we turn to Spark structured streaming. We take a stream of the flight position data, we combine that with our aeronautical data. We filter just to the stuff that's at an airport, on the ground, and then we group it by a flight, and we aggregate a taxi event. Aggregate just by combining lots of data. We produce taxi events as a result of that. And in order to talk about how we actually do that, I want to talk about streaming aggregation, because I think this is one of the best features of Spark and of working with Databricks. So everyone should be familiar with how you aggregate a batch of data. The canonical example is an average. You take in a list of numbers, you divide the sum of that numbers by the number of numbers in the list, you get your average. Very easy, might depend on a bunch of rows of data, gives you one row out that describes the aggregate of that data. That's all well and good while you're working with small amounts of data. As soon as your data starts to be large, maybe arrives over time, maybe doesn't fit in memory at all, maybe you don't know when the end or when you've seen the last value, this doesn't work as well. And that's where streaming comes in. So here, the approach is a little bit different. You create a class or something that can hold some state. In this case, very simple. You just need to hold the sum of all the numbers you've seen so far and the number of numbers you've seen. And now, whenever a value comes in, you can then update your sum, update the count of values that you've seen, return the average. So this would look like this, where you create an averager, and now you pass in numbers, and eventually you get to the same answer after seeing the same data. But you never had to see all the data at the same time. You could fit a lot of data in here. This silly example is now an infinite averager until you overflow, I guess, your sum or your count. So how do we do this on Spark? Well, we use flat map groups with state. It's just a superpower. So it works very similarly. You group your data on a key or an ID that you want to keep track of. You define a function to be called on that group that accepts the previous state, if there is any, or creates it. You update that previous state based on any data you see in that batch. You can then omit anything that you need to. So it could be temporary results, interim results, whatever it is, in our case, taxi events. And then you set the state timeout. So that if you haven't seen data for that key for that amount of time, Spark knows it can drop the state, and that bounds the memory required for this aggregation. So if you can have enough memory to deal with all the data that's going to arrive at any one point in time, you can aggregate an endless supply of data. So you pass that function over flat map groups of state, and you're off to the races. Now, what kind of function could we use? I've been told I can't talk too much about it, but I could say that we could do some interesting filtering to get rid of noisy data, and you could maybe implement a state machine algorithm that could do whatever computation you want within this. So we aggregate this taxi event data, we join it together, and we produce a taxi event. This is just a representation of an aircraft taxiing from a stand to a runway, or from a runway back into a stand. You'll get things like the direction, so taxi in or out. You get a duration in seconds, how long it took, obviously start and end times. We can estimate the distance in meters, and then finally we can actually pull out the route that the aircraft took. So we can say, oh, it left from stand 76, taxiway S to M9, and then took on 26 right. That's the kind of data that we can create for one aircraft. And in fact, right now we do that for about 80,000 taxi events every day that we can detect at airports around the world. Okay, so we have taxi events. Now what? Well, we'll throw them into a database. We'll create a little API around it. And now we can start serving them out to pilots. And that's what we did. That's what we started back a little while ago. We showed the data to pilots. So the pilots will open FliteDeck Pro. The app queries our API. It grabs recent taxi events, shows them to the pilot. The pilot makes an informed decision. Bob's your uncle. Off to the races. We should make better decisions, enabling pilots to make better decisions. And we're just showing them the data that they know already. We're not, we're letting them make the call. We got some good feedback. And we also got some feedback of, well, not so simple. So a great example of this is at Dallas-Fort Worth. You get banks of flights that depart simultaneously. They'll all push back within a few minutes of each other. And you'll go from having a 5-minute average taxi out that is bounded by how long it takes the aircraft to get from the stand to the runway to a very congested taxi out that is no longer bounded by the time, but is now by the resource constraint of the runway, because you have aircraft queuing to take off on that runway. So our idea that what just happened will help pilots make that decision is only partially right. Pilots will need to know a little bit more about the context of what to expect at this airport at this time of day. Great. We have historical data. Data scientists, we put on our data science hat. Let's go figure out what happened historically. Let's iterate, right? That's what we're supposed to do. The only problem is, at this point, we'd only been collecting data for a few months. So we had, a couple months of taxi events. We really wanted to understand seasonality. We want to look at what's happened, this time last year. At least need a year of data. Probably want 2 years of data. But we've only been generating it for a few months. So we could wait, in 2 years of data, we'll have 2 years of data. But that's probably not going to be the best option. What we can do is we can backfill. So we can take our source data, we can add more position data to that table. This is in Delta, so we're just, filling up those earlier partitions. And then we want to be able to transform them again. And so we have a few options to do that. We're doing a streaming algorithm, so we can use trigger once to tell the Spark to grab everything that's new in that data, run it all through the algorithm all in one batch. That requires all the data that we've just backfilled to fit in memory, which I guess we could probably build up enough of a cluster that would work. But it's an expensive process. It's an all at once. We could try to partition it, and we could go day by day or period by period. But we don't have a nice aggregation like you might have in a data warehouse where you just want to know the taxi events on Tuesday. Aircraft don't care about dates. You start your flight at 11 p.m. on one day, end it at 2 a.m. the next day, UTC time. Now your by date aggregation doesn't work at all. So you could do something where you then say, well, we're going to load up 3 days of data. We're going to do it all. We're going to take the events that fall in the middle data. We'll write that in there. And then we'll throw all the stuff on the edges. That was just to make sure that we got rid of the ragged edges on either side. We've done that before. Not the most elegant solution. You end up processing about 3 times more data than you need to. The final option is we can replay our stream. And this is obviously the right choice. But there was one little wrinkle. As long as you play the data in order, Spark Structured Streaming will send the data through your algorithm in the same order, and you are guaranteed to get the same results, regardless of your batch size. But we had just written data into our source that was written, that occurred afterwards the write occurred afterwards, but the data, an event time was before the data was already written there. And by default, when you stream out of Delta, you stream based on the commits. So we would stream the red data first, Then we would stream the blue data, and using our watermark, we would drop all the blue data and say, well, that's really late. We don't care about it. But there is a great option, and we were one of the previewers of this. I worked with Databricks on it, which is using this with event time order option to preserve order regardless of when you wrote the commits. So now Spark can say, use this time, use this column that contains my time, and it doesn't matter when that data got written in, process it across that batch, or that time dimension. And Spark will actually chunk it up into pieces and feed it into your structured streaming algorithm in that order. That's great. We can provision the compute we need. We can run in just a few hours, several years of data through this algorithm, as if we'd seen it for the first time. This is not only helpful, for a situation where you're backfilling from scratch, where you had nothing there before. It's also really helpful if you realize that you made a bug, which we've made bugs. We've realized that something about the algorithm was wrong, or we wanted to say well, let's not only identify when the aircraft pushes back, but let's figure out when it starts moving forward under its own power. So it's great. We can start doing that now. Now we can also go backfill that data and create that data again for historical data. So now we are armed with our historical data. We went and did some modeling. We start with a really straightforward model, which is we just want to predict the distribution of durations at any point in time. So you can ask us for what's the average at Dallas-Fort Worth, and we'll just provide back all the average, the distribution of every event we've seen so far. And we can start building a model on that that's just using like a Bayesian model, right? That's just conditioning on, well, what about all the data there going to runway 17 right? What about all the data from going to 17 right coming from terminal C? What about all that at this time of day? And we can start conditioning that distribution on just the information that's relevant at any point in time. To figure out what things are relevant, we tracked experiments in MLflow. We can use this traditional machine learning error metrics to figure out how well our distribution approximates that data. And we can deploy that. So now we have a model sitting in Kubernetes that was trained here, and now we can expose that extra endpoint and we can provide additional context. And so now what we're showing to pilots and what's in beta right now is not only the current duration, but we also provide expected durations. So a little Spark chart of what we'd expect to see, what's normal at this time of day. And how am I doing for time? I'm doing well for time. Okay, good. Then I want to try to show a demo. And I know demos haven't always gone smoothly today, so I'm a little nervous. We'll see how it goes. This is FliteDeck Pro. This is the iPad app that pilots use. This is a beta version of the application that's got a few features that are not widely rolled out yet. I have a flight in here. That flight is going from San Francisco. It's going to take me home to Vancouver on Friday. I've got my route in here, and now I can tap over on my runways and I can see what information exists. So right now we've got departures on one left and one right. I know that I'm going to be going on one right. And then I can go over to my info and I can start seeing what departing traffic looks like at this airport. If I tap on, oh, and it just refreshed, perfect. The Wi-Fi works. So if I tap on this, I can see right now that we usually expect about 10 minutes of taxi out across the airport. Right now we're seeing about 7 minutes. And I can even go down and I can start looking at recent clearances. So I can see this aircraft from D6 just taxied out. It was a Embraer 10 minutes ago. It was about a 4-minute taxi. And you can see that was SkyWest 3347. We can keep going and find another one that's a little further away. That took 10 minutes, 14 minutes ago. That taxi occurred. And you can actually see the route that the aircraft is traveling. So if I know that I'm going from F21, as a pilot, I could come in here and I could say, okay, great, I know I'm in F21. And now, not only do we have all the departing traffic, now we have the estimate of what's happening from F21 based on activity at F21 and nearby stands. And we can see, while the airport itself is operating a little bit faster than usual, we would expect around 12 minutes from F21 out to one left. So we think that kind of information gives pilots the guidance, the confidence they need in order to make an informed decision themselves. It just presents the data as it is without a lot of guidance. We just want to tell them, here's the situation, you make the best call. So, what else can we do? Well, we started, right? Can we do the clicker? Yes. Okay. So what else can be observed? Well, it turns out this pattern doesn't just work for taxi events. There's a lot of things that once we start combining aircraft position data with maps, we can start seeing what the aircraft is doing. So right now, we have a few things that are out there. We can do stand arrival and departures. Runway arrival and departures, those come with taxi events. We can start doing things about de-icing, so we can tell the aircraft is on a de-icing pad, how long it's been there, what the time is from when it got to the de-icing pad until it took off, to understand the holdover time. We started detecting airborne holds by noticing patterns where the aircraft is circling. This was at a time where there were some thunderstorms in Dallas that were causing a lot of holds. We can detect when the aircraft ends up diverting to another airport, stops making progress towards its destination, is now going somewhere else. We can tell the possible diversions coming up and give a quick update on that. And when we stop just looking at the flight, but we then take those things that we detect about a single flight, like this flight landed on this runway, this flight took off on this runway. Now we can take those events, we can group by airport, and we can say things like, well, what are the active runways at an airport? So we can tell you that there's departures on runway 5, arrivals on 5 and 6 right. We can also say things like, how many aircraft are taxiing out right now? Because we can see which aircraft are in the taxi state, moving towards a runway. We think this is exciting. We're still figuring out what to do with all of this, where it's going to go. We don't want to throw decisions or more data at people. We don't want to throw more dashboards at people. We want to really target decisions that matter, put this in a place where it comes up when needed. So we're still working on that. But as we've been doing this internally, a lot of folks around Boeing have noticed that, hey, this data is kind of cool. We think we could use this for what our team does at Boeing. And so we started producing some data products for folks based on this. So the marketing team, figuring out trends, making forecasts based on flight hours around the world. Engineering, understanding the flight characteristics of aircraft. It's been part of the process of certifying the 777X. Simulation, fantastic input if you want to simulate, because you get all the events that are going to happen in your discrete event simulation. It's been useful for consulting because we can talk about what's happening at an airport, what's happening with an airline. We've helped a few airports understand, a serious weather event or something like that, and what the changes in taxi time were, where the hotspots were, things like that. And then, of course, it's useful for AI ML features that other teams are using, where you want to understand congestion, or you want to understand delays, and it becomes an input to other products. And that's great, but right now we have an API, and that API says, here's the latest taxi events at this airport, which is useful, but it's not useful for this use case, right? Now I want to say, give me every taxi event for this aircraft. Give me all the data for this airline. Give me everything in this region. And now we're talking about years of data, gigabytes of data that don't fit through, a REST API interface. So how do we share bulk data? I feel like everyone should know where this is going. Unity Catalog. So it's been great. We've started the adoption of Unity Catalog within Digital Aviation Solutions. We've got catalogs set up for a bunch of different teams that all produce different data products. So our aeronautical data and our maps, weather data, from METAR and TAF, which are, I guess, for anyone who's not in the aviation world, text weather formats that pilots use. The flight events that I've been showing you, and quite a bit more that's going in there. It works well for us because we have distributed ownership. So I'm responsible for my data and the data product that we expose, but we don't have to go through a central place to do that. Pretty easy to share, especially within a region. And it even offers multi-cloud support, so we can share between regions or between cloud providers for those use cases that need it. One of the things that's been really helpful for our team as we've been developing is we think of our data development, and then we build applications on top of it. And so we think you deploy a new data thing that you're building, a new data product into dev first, then you promote it to UAT, and then you get it to prod. You're really excited. You go to build the next thing that uses it, and you're in your dev environment. You're like, well, I don't want to build on the dev data product. We have a good data product, it's in prod, right? But the definition of that product is just a table somewhere, right? And so you now need to figure out, well, how do I get the dev the dev service principal access to that prod location? Maybe prod is in a different subscription or VNet. You can't make that happen easily. And so moving to Unity Catalog, where now the dev data goes into the dev catalog and the dev environment has read-write access to it, we now have a UAT and a prod catalog, and the dev environment has read access to it. So it helps our development a lot because we can always use the best data that we have available across environments, across workspaces, because we're no longer sharing data locations, we're sharing tables. So that's our journey so far. I wanted to say a couple thank yous to the development team, a lot of folks who've been working on this over several years at Boeing, and to our fantastic counterparts at Databricks who've been helping us here. And because of the developer conference, I wanted to share a couple lessons learned personally. So first, development is iterative. You really need to get something out and get people to use it to get feedback, because your hypothesis of what's going to work is almost certainly wrong. So try again. That development is iterative is also really helpful because we often find that there's no one business use case that's going to justify all the investment as you get started in data, because there's a lot of overhead. But as you start building up, things move faster, and now to get to the next product, you don't have to do all the CI/CD, all the monitoring, all the support. Now you're just adding an additional instance of what you already know how to do. So develop iteratively, get something out, tackle one amazing or one useful use case right away, and then move on to the next thing when you can. And then finally, stateful streaming is fire. It's fantastic. If you're not using it, go find out about it. It's good. If you want to know more, we have, you can go to developer.boeing.com. We've got APIs up there that show the same data that I just showed on FliteDeck Pro to anyone who's interested in using it. We have about 400 supported airports that cover about 67% of global commercial traffic. Yeah, thank you so much. Appreciate it.
Thank you, Will. Let's give a big round of applause.